Okay, boys. So today we will discuss about a new topic which belongs to Wheatstone Bridge, but it has another name. It is called meter bridge. So first, I will explain about the meter bridge. I will draw a circuit first, and then I will give the explanation. All of us should draw the circuit first. Okay, first we draw this circuit, and then I will explain it to you about how the principle of meter bridge works. Okay, so this is the circuit. It's quite a complex one, but it's actually a Wheatstone bridge. How it becomes a Wheatstone bridge, I will explain to you. First, just you draw the picture. Okay, so we can start from here. Though it's a meter bridge, but it is a kind of Wheatstone bridge. But how we can say it's a Wheatstone bridge? Because we know that Wheatstone bridge consists of 4 resistors. We see here 2 resistors, and how the combination like meter bridge and Wheatstone bridge are same. So here first I will draw a Wheatstone bridge. Just like this, we have drawn the Wheatstone bridge on the previous class. The 4 resistors and the diagonal point consists of galvanometer and key and cell. So these are the 4 points: A, B, C, and D. So this is P, Q, R, and S. So on the left side, the circuit diagram is Wheatstone bridge circuit, and on the right side is the meter bridge. So we have to compare these 2 circuits. Okay, first, if we see the diagonal point B and D, there is a galvanometer is included with this point. And also, if I look into this point, this is B. All these sections are considered as B, and this is D. This point is considered as D. So in between the point B and D, also there is a galvanometer is connected, just like this. Also there is a galvanometer which is connected in between point B and D. Okay, so this is the first comparison. Again, the opposite diagonal point A and C, there is a key and a cell or a battery, you can say anything of it. So the opposite end consists of a cell and battery, and also this is the opposite end, A and C. This whole section is A, this whole section is C, and it contains also a key and a cell. So this can be said as the meter bridge is completely a Wheatstone bridge. But now we have one question left, that is Wheatstone bridge has 4 resistors, P, Q, R, and S. But meter bridge, we have seen only 2 of it, P and Q. So where the R and S resistance? Here the R and here the S resistance, which can be found in the meter bridge wire. If we say here point A to point C, there is a wire which has a length of 100 centimeter, or you can say it as 1 meter. That's why the bridge name is meter bridge, because 1 meter is 100 centimeter. So in here, the resistance R and S will occur. Okay, then what? If I indicate this symbol, there's an arrow sign here which I indicate at point D. This arrow sign has another name. It is called jockey. And jockey is just like a pen which has wire connected on it. And if I touch this jockey at point A, the galvanometer will deflect on the left side. And if I plot jockey on the right point, the galvanometer will deflect on the right side. So there will be two-way deflection when I touch the jockey at point A or at point C. But there will be a point, definitely there will be a point where the galvanometer shows its zero deflection. And that point is considered as D. Suppose I am touching this jockey at point A. The galvanometer is on left side. And when I touch it on point C, the galvanometer deflection on the right side. But if I go from this wire, the deflection, there will be some point where the deflection, there is no deflection for the galvanometer. It is called the zero deflection. At that zero deflection point, we will get point D. Because if the galvanometer gives us zero deflection, this means that there will be no flow of current through the galvanometer, or the galvanometer current is zero. So this is called zero deflection. And when we get the zero deflection, the left side we can say there is R, and on the right side there will be S, which is occurred on that wire. So in such a way, a meter bridge works. But we use the meter bridge in our experiment or in our laboratory for some experimental value. We just determine for unknown resistance. Meter bridge is used to determine unknown resistance. Suppose you are given an unknown resistance at P or Q, meter bridge will detect it. What will be the value of unknown resistance? Okay. Now, how we can get the equation for a meter bridge? Let's start with AC. If I say AC is the meter bridge wire, it is the meter bridge wire. Meter bridge wire, and it can be said as 1 meter or 100 centimeters. So here AC is the meter bridge wire, which is 100 centimeters. And when we get zero deflection at point D, for zero deflection, at point D, I can say AD, we will consider AD as L centimeter. So CD will be 100 minus L centimeter. I'll remove it from now. So CD is 100 minus L centimeter. And now if you look into AD and the value of CD, you see that they are in length formation, but we have to convert it on resistance formation. So how we can convert a length into a resistance? Length into a resistance, if we want to convert, then we have to introduce another quantity here, which can convert the length into resistance. And that quantity is resistance per unit length. Resistance per unit length. We consider resistance per unit length as sigma. So first, we consider the resistance per unit length is sigma. Okay, so if I say resistance per length L per unit length sigma, then L length of the L sigma. So L sigma we can consider for resistance of L length. And that L length resistance is R. So in such a way, we can convert a length into a resistance by multiplying it resistance per unit length. So We have got R, the value of R. So we can also get the value of S. Resistance per 100 minus L length. So it will be 100 minus L into sigma, and that is called S here. So both the R and the S in the form of resistance we have got now. Now what? We know meter bridge works as a Wheatstone bridge. So the meter bridge principle is also just like the Wheatstone bridge principle. What is the Wheatstone bridge principle? On the last class, we have said that Wheatstone bridge principle will be P by Q is equal to R by S. This is the Wheatstone bridge principle. And now if I plot the value of R as L sigma and the value of S as 100 minus L into sigma, then I can get another equation just like this. P by Q is equal to L by 100 minus L. So this is the required equation for meter bridge, and with the help of this equation, we can determine the unknown resistance which is placed on that meter bridge, and we will get the value of it by the zero deflection point. Okay, so we have our equation on the board, and now we will do some mathematical problem of it. Okay, let's start with one mathematical problem. Turn off your microphone, please. Everybody turn off your microphone. Okay. Okay, so here the math comes. In a meter bridge, on the first arm, 10 ohm, and on the second arm, an unknown resistance. On the second arm, an unknown resistance is placed. Full stop. The zero deflection for galvanometer is found at, the zero deflection of the galvanometer is found at 20 centimeter from the right point of it. 20 centimeter from the right point of it. Calculate the unknown resistance. The zero deflection point is found at 20 centimeter distance from the right side, the right point of it. Find the unknown resistance.
Sir, 40 ohm.
You have already solved it. 40 ohm. Okay, I will give some time to others. Whether it will be correct or not, we will get it. Okay, so I will give some hints for those who will not able to understand this kind of math. Here there are two distances, one from the left side and another from the right side. If I say A as the left point, then C will be the right point. Now I am giving you that the math said that 20 centimeter from the right point of it. So you can say here CD as 20 centimeter. You don't need to convert it on meter because we have used in centimeter form. Or you can say CD as 100 minus L. So 100 minus L is equal to 20 centimeter, or L will be 100 minus 20. So L will be 80 centimeter. Now, if you plot the value of L, the value of 100 minus L, and the value of P, you will get the value of Q. So it's the easiest one. And you will get the answer as 40, right? Is it the answer 40?
Yes, sir.
Okay, so this is the meter bridge mathematical form. And if I say, for just like the right, if I say the left point, then you will consider it as L, and then you will reshuffle it, and you will get another answer for it. So you have to remember one thing, whether the distance is given from the left or the right side. And then you can solve the math. That math will be perfect for you. And it will be correct. Okay, thanks. So this is for meter bridge. And now we'll go for another topic, which is most important to us. Okay, so it is called Kirchhoffs Law. Kirchhoffs Law. Somebody can say it also Kirchhoff. The both names are correct. Kirchhoff or Kirchhoff. Both names are correct. So Kirchhoffs Law is a very important for current electricity, because when on the SEC, during the time of our SEC, we have done our circuit in the form of Ohm's law. We have used Ohm's law when we solve the circuit. But Ohm's law has some limitations, because if I give you more than one cell, Ohm's law sometimes cannot detect, cannot solve that circuit. But Kirchhoffs law is totally appropriate for this kind of circuit. 2 cell, 4 cell, 5 cell, Kirchhoff can solve you easily. That's why Kirchhoffs law is very important to us, to solve the circuit which contains more than 2 cells. Okay, so Kirchhoffs law has, in fact, 2 laws, first and the second. First and the second. And the laws are a very easy one. The first one and the second one. And we know both the quantities here. If I say I, it is current. If I say E, it is electromotive force. So, but how we can write it? So here we start. First law. First law. You go with first law. Okay, start. The summation of total current on a certain point of a circuit. The summation of total current on a certain point of a circuit is considered 0. The summation of total current in a certain point of a circuit is considered as 0, or you can say is 0. I can explain it to you, but we will do the explanation after we have written the second one. Okay.
Sir, will you please again?
Yes.
Sir, will you please repeat again?
Saad, I can't hear you properly.
Sir, will you please repeat the law again?
Oh, okay, I will repeat it. The summation of total current. The summation of total current on the certain point of a circuit is 0. the summation of total current on the certain point of a circuit is 0. Okay, so now for the second, we will go for the second Kirchhoffs law. The summation of, now it is for the second law, the summation of current and its individual resistance. The summation of, you can also use another word, product. You have to use it, product. I have forgotten it, now you will use. The summation of product of current and its individual resistance in a circuit. The summation of product of current and its individual resistance in a circuit is equal to the electromotive force is equal to the electromotive force of the circuit is equal to the electromotive force of the circuit. Okay, I will repeat it again. The second law for the last time. The summation of product of current and its individual resistance is equal to the electromotive force of the circuit. So here on the second law, which I give to you, that summation of the E as 0, and I have told the law, you have some mismatch here, but I will rather explain it to you. And first we will go for summation of I equal to 0. How summation of I becomes 0? Here I will consider a wire, 5 wires in fact, and they are connected in one common point. This is the point. And if I say I1 current flows from here, I2 flows from here, I3 from I4, just like this, I have just we assume that the current flows in such direction at this point. So according to Kirchhoffs law, there will be no storage of current in any point of the circuit. There will be no storage for current. So if I say there will be no storage for current, then I can say the summation of I is considered as 0. So the current that goes from one point to another point, or they will meet at the same common point, that common point will never store any current of all of the wires. So this is the main thing. If I consider this point will store no current. And if I consider I1, I2, these two currents are coming to that point, then I can consider I3, I4, and I5 will go away from that point. So if I say the current which is coming to that point as positive, then the current which goes away from the point is negative, then the total summation of the point is 0. That is summation of I. And if I say I1 plus I2 as I3 plus I4 plus I5, then we can say one thing. The current that comes to the point and the current that goes away from the point, that their summation are same. So I1, if I1 and I2 is 5 ampere, I3, I4, and I5 also have the value of total 5 ampere. So this is Kirchhoffs' first law. Okay, so now for the second, how we can understand the second law? If I say the summation of electromotive force is 0, and on the second law that I have told to you that the electromotive force is the summation of product of current and resistance, these two statements, firstly, we don't understand about these two statements, whether the two statements have similarity. but I will prove to it that summation of E is equal to 0, how it becomes summation of E equal to 0. The second statement you have already learned on class 10 by using this equation. I is equal to E by R plus R. Also, you have learned this equation when we are solved the combination of cells. We have also used this equation. If I say, what is the value of E here? You can say it as IR plus I small r. So I capital R plus I small r, we can say these are the product of current with individual resistance, product of current with individual resistance. And also there is a summation because we are adding it. So the summation of product of current and individual resistance is equal to the electromotive force of the circuit. Now what? If I say E minus IR equal to 0, then this E minus IR can be considered as summation of E. So this is the explanation. Because IR, the product of current and resistance, is equal to the voltage. You know that from Ohm's law. And E is the electromotive force, also known as the voltage. So the summation of all voltage or the summation of all electromotive force in a certain point is considered as. So these are the two laws which is very important to us when we do some Kirchhoffs circuit as well as uses of Kirchhoffs law in other circuits. Okay. Now we will go for Wheatstone bridge again. Wheatstone bridge, we will go for the Wheatstone bridge explanation again, but this time I am not using the Ohm's law. On the previous class, I have discussed the Wheatstone bridge principle by using the Ohm's law. But here, I will use the Kirchhoffs law to solve the Wheatstone bridge principle. So now we will go for it. Okay? So we will write now Wheatstone bridge principle according to Kirchhoffs law. Wheatstone bridge principle according to Kirchhoffs law. Okay, I will turn off the right corner right so that you can see the topics properly. Wheatstone bridge principle according to Kirchhoffs law. Okay, so how we can say the Wheatstone bridge principle by using Kirchhoffs law? First, we will draw the Wheatstone bridge circuit. So here the Wheatstone bridge circuit, I will draw for you again. All of us will draw it. Okay, so here are the 4 points. I'm indicating the points as A, B, C, and D. And also, I am giving the direction for current in this whole circuit. I consider it is I1 here, I2, I3 here, I2 here, and I4 here. And I am also give the resistance here. Okay. So the circuit is almost the same circuit that we have drawn on the last class. But now there will be slightly different in this circuit diagram because you will see no voltage point here. On the previous class, if you see into this diagram, I have written some VA, VB, VC, VD, this type of thing. But now I am not writing any of these because we are using here the Kirchhoffs law. And using the Kirchhoffs law, we will solve this circuit. So how we can solve it? First, we will go for a condition. The condition is just like this. VB is greater than VD. We'll go for this condition. Why? Because we assume that this is not a Wheatstone bridge circuit which maintains the Wheatstone bridge principle. It's a Wheatstone bridge circuit, but it's not maintaining the Wheatstone bridge principle. We will consider first this thing. So when there is no Wheatstone bridge principle in a Wheatstone bridge circuit, at that time there will be one thing happen. Either VB is greater than VD or VD is greater than VB. So we will consider just one of it. VB is greater than VD. So we can say that in this time, the principle is not in this circuit. The Wheatstone bridge principle is not in this circuit. So another current flows through the galvanometer. And I indicate this current as IG. So this is the circuit current direction. Now we can say, we can go for Wheatstone bridge to prove the Wheatstone bridge principle. First we will use for Kirchhoffs first law. We go for point B. If I look at point B, some current goes away from it, some current goes towards it. If I say at point B, I1 is the current which is going towards point B, and I3 and IG are the two currents which go away from point B. So I can say I1 as positive, I3 and IG as negative, and the summation of I is 0. So how I can say it? If you look into the diagram, you have to maintain one thing, that if any current goes towards that point B, you will consider it negative, positive. Then the current which goes away from point B, you will consider it as negative. So the current in opposite direction is negative and the current towards the direction is positive. Okay, so at point B, I can say I1 minus I3 minus IG is equal to 0. So at point D, if I look at point D point, so I can see that I2 current goes and IG current goes towards point D, and I4 goes away from point D. So I2 and IG can be considered as positive and I4 is negative, and the summation of it is 0. So these are the Kirchhoffs first law, and according to Kirchhoffs first law, we have got these two equations. I1 minus I3 minus IG equal to 0. I2 plus IG minus I4 equal to 0. Okay, now we will go for an enclosed circuit. And what will be the enclosed circuit here? Suppose I am giving a circuit A, B, D, A. If you look the circuit point A, B, D, A. So you are starting from point A, then go B, then D, and after that you will return to that point again. So it makes an enclosed circuit, which is A, B, D, A. And also, if you look in the section of this circuit, I am giving you that in such a way that the left side, look into the circuit A, B, D, A. In the total path, there will be no source, or you can say no battery is connected in this total enclosed circuit. So when you find no batteries connected in an enclosed circuit, then there will be no electromotive force. So how you can say it? Just like this. You go from A to B. Current I1 is also go from A to B. So the current is I1 and its resistance is P. So the product of current and resistance is I1P. Then the second path, BD. You go from point B to D, and the current IG also goes from B to D. So the current is IG and its resistance is G. And the last one, you go from point D to A. But now you can say that you are going from D to A, but current goes from A to D. So the current direction is opposite of your direction. you can consider the current as negative and the resistance is R. And you have completed the whole path, but there is no source in the whole path. The source is outside the path. That's why if there is no source, the source is zero. If there is no source, you can say the source is zero. This is the second combination. And you will find I1P plus IgG minus I2R. This is the Kirchhoffs second law explanation. Okay, now I am giving you another enclosed circuit on the right side, just like at the left, the right side. And I am giving you just like this, B, C, D, B. So you start from B, C, D, B on the right side of the circuit. Now, can anybody say what will be the formula for BCDB enclosed circuit? Anybody? You first go from B to C. What you have got?
ISQ minus IgG
I3Q.
minus ISS.
Okay, so first I3Q, that will be correct because I am going from B to C. Then I am going from C to D, but current goes in the opposite direction. So it's minus I4S. And I am going from D to C because D to B, B, C, D, B. I am going from D to B and current goes in the opposite direction. So it's minus IgG. That will be zero. So the first law and the second law, both law we have discussed in the Wheatstone bridge circuit. And we have got 4 equations of it. First 2 for the first law, the last 2 for the second law. If I consider these 2 equations for the first law and these 2 equations for the second law. Now, what we will go for? Here, I am giving you that the condition is VB is greater than VD. And then you have discussed all of these things. I am giving to you VB is greater than VD. That's why you are going for this. But the Wheatstone bridge principle says that VB is not greater than VD. What is the principle of Wheatstone bridge? Principle
VB
of,
equals to VD.
yes. Principle of Wheatstone bridge is VB is equal to VD. So if I consider VB is equal to VD, there will be no galvanometer current. There will be no flow through the galvanometer. So the galvanometer current is also zero for the condition of Wheatstone bridge principle. So according to this condition, I can say Ig as 0. So if I say Ig as 0, this becomes 0. Also, Ig becomes 0. Here, IgG, the whole terms become 0. And the last, minus IgG, the whole terms become 0. So I'm giving the circle so that you can consider it as 0. So the equation, how the equation looks like now. I1 is equal to I3. If I place Ig as 0. I2 is equal to I4. If I place Ig as 0. I1P is equal to I2R. If I place Ig as 0. And I3Q equal to I4S. If I place IgG as 0. So if I remove all these Ig from the 4 equations, the equation looks like this. I1 is equal to I3, I2 is equal to I4, I1P is equal to I2R, and I3Q is equal to I4S. Now what? I1 and I3 is same. I2 and I4 is same. So if I divide this equation by this one, I1P divided by I3Q equal to I2R divided by I4S. Then I1, I3 I can remove from it, and finally I can get the principle. P by Q equal to R by S. So in such a way, Kirchhoff can explain all the circuits that we have learned on our SSC or we will learn on our higher classes. Kirchhoff can solve all the circuits. That's why Kirchhoff is more important than Ohm circuit. Okay, so this is the starter. We have done our law, Kirchhoffs law, and we are explaining the circuit here. But on the next class, we have 3 classes in each week. On the next class, I will go for the Kirchhoff circuit, to how to solve the Kirchhoff circuit, how you can get the value of current, the value of voltage from it. So the next class will be Kirchhoff circuit class. And if you have any questions for today's class, you can ask me now, or I will stop the class for now. Is there any question for any of you? You can ask me. Okay, boys. So thank you. We will go for the Kirchhoff circuit on our next class. I'm stopping the meeting now. Stay home, stay safe.
Okay, sir. Assalamualaikum.
Walaikum salam. Allah Hafiz.
Assalamualaikum, sir.
Assalamualaikum.
Walaikum salam. Allah Hafiz.